Hi, this is the energy knowledge test. Right. Question number 1 is list 8 energy stores. Now these stores you kind of need to know, right? So if you could think of then a way of remembering them, then obviously that's going to be beneficial. The first one is chemical, okay? So something like in food, right, or in a battery. The second one is gravitational potential energy. Okay, so that's anything that's kind of away from gravity. So if you move something up and away from gravity, right, that's got gravitational potential energy. Kinetic. Kinetic is kind of like movement energy. So my hand moving across here has got kinetic energy. Thermal energy is to do with temperature. Elastic is energy that is then stored within an elastic band or a spring. Nuclear, magnetic, okay, and then the final one is electrostatic. Okay, so electrostatic is when you kind of build up static electricity, something like a shopping trolley or in a car or on the Van de Graaff machine. They're kind of, so what they are is they are then the 8 energy stores. This is how energy can actually be stored in something. Now question number 2 is list the 4 Herm energy transfers and explain what they are. Now Herm is the way of kind of remembering it. These are energy transfers. So we've got the stores that we talked about before. Herm is the transfer of energy from one of those stores to another store. All right. Now the first one is heating. The second one is electrical. The third one is radiation. And the fourth one is then mechanical. All right, so what we've got is we've got Herm, where we've got heating, electrical, radiation, mechanical. Now what you've got to do then is you've got to know how they actually transfer, right, the energy itself. So heating is transferred by convection, conduction, and radiation, right? And we'll talk about those in a later question. Electrical energy is basically from a power source. So it's from a power source, and then that is then transferred to a component. Right? So for example, a cell or a battery. Radiation, right? So radiation, the two ones that are the transfers here are light and sound. And then the last one, which is mechanical, right, is when a force acts on an object. Okay, e.g. a collision. Right, so just to summarise that again. So what we've got is we've got all the energy stores on the previous one. Herm is how they transfer from one store to another. So heating can be transferred by convection, conduction, and radiation. Electrical comes from a power source, right? And the power source sends electrical information or electrical energy to a component, for example, a cell. The transfer of radiation is in the form of light or sound, and mechanical is when there's a force. My writing is terrible there. Collision, object. Okay, so that's question number 2. Question number 3. What are the definitions of the following? All right, so what I'm just going to do is I'm going to go through some definitions, all right, that are kind of the most important ones within the topic. Dissipate is to scatter in all directions. Okay, or it can be sometimes put as wasteful. Right, so really what that means is, right, if I'm going to dissipate a class, what they'd do is they would just kind of scatter in every single direction possible. Principle of conservation of energy, that is then when the amount of energy stays the same. Okay, so where the amount of energy stays the same. So within kind of some sort of area or a system, right, the conservation of energy is where the amount of energy stays the same. There's always the same amount of everywhere on Earth as well. Work, right? Work is the transfer of energy from one store to another. Transfer of energy from one store to another. Okay, so me doing this writing here now, what I'm doing is I've got chemical energy inside me and it's getting transferred, right, by me doing work. Power. Power is the rate of energy transfer. Okay, measured in watts, right? So realistically, if you've got a 100-watt light bulb and you've got a 1-watt light bulb, right, the 100-watt has got a greater power, so then what it can do, it can transfer energy at a faster rate. Efficiency. It is the energy usefully transferred. Okay, so if you think about electricity going into a light bulb, what's the useful energy is the light, and the heat is then not useful. So efficiency is basically the percentage of energy that is usefully transferred into light. A non-renewable energy resource is finite and it cannot be replenished. Okay, so finite means it's going to run out at some point. Renewable is infinite. And that is then when it can be replenished. Okay, so think about wind, right? It's basically infinite, there's always going to be wind. Question number 4, all right? What are the 3 ways heat is transferred, and explain each one. Now these are then the ones that we talked about before. So what we've got is we've got convection, we've got conduction, and we've got radiation. Oh my god, my writing is terrible. Okay, convection. Convection is the mass movement of particles often up. Okay, that's when the people say heat rises, right? Because convection currents is where the heat goes up. That's convection, right? It's often the best way of thinking about it is that heat rises. So what I might do is I might just put down there heat rises. Conduction, right? Conduction is where there is direct contact. So if I've got a spoon in a cup of hot water, right, the spoon then will conduct heat through it. And if I touch it, then I get conduction from the spoon as well, because I've got then direct contact. And the last one of these is radiation, which is the electromagnetic spectrum, or electromagnetic radiation is probably better. Okay, so that's kind of, if you're stood in front of a fire, what you can do is you can feel the heat, and that is then by radiation. Right, you've got fire, you've got convection going up, right, heating the top of the room, you've got radiation coming out, and then if you've got anything in it, there's then conduction going on. Okay, examiners love this question because specific heat capacity sounds posh, right? It's got a good definition and it's also got interesting units. So specific heat capacity is the energy needed to raise 1 kilogram of substance by 1 degree C. All right, so that's kind of like the definition of it. Now, what we've also got in here, you need to know the units. Energy, joules. Kilograms, degrees C. So the units are joules per kilogram degrees C. Okay, good set of units. Question number 6. All right, how does a power station generate electricity? All right, so what I've done here is I've just done it into a flow diagram. And how does the national grid transfer electricity across the country? So a power station. Okay, so what I'm going to do is, now this is going to be a little bit small for me, so what happens is we release energy. Okay, so that is then whatever it is, coal, oil, gas, power station, and what you do is release energy. Then you create steam by water boiling. That then turns a turbine, okay, which kind of looks a bit like a windmill. And then what happens is the turbine turns, I'm never going to fit this one in, a generator. And then the generator induces voltage, which basically means it makes electricity. The national grid transfers energy from the power station. That's where it all kind of starts. All right. It then goes to, I'm going to have a cheat here, a step-up transformer. It then goes shooting across the country via pylons. Then when it gets to wherever it's got to go, it then goes down into a step-down transformer. Nearly made it in the box. And then it gets to the house or the factory. All right, and that is then the electricity that's getting sent across the country via the national grid. Now, question number 7. Name 5 ways heat escapes from your home and describe how you reduce this heat loss. So what you need to do now is you need to think, just picture your house, right? Where do you think heat is actually getting lost? First one is through the walls, right? So literally heat can get through the walls, right? You wouldn't imagine it, but it can. One of the best ways of solving that is cavity wall insulation. Okay, so what you've got is you've got brick wall number 1, brick wall number 2, because your house has kind of got 2 layers of bricks. And what they do is they fill here with foam, polystyrene balls, whatever it may well be. And the idea then is to stop transfer of heat from this side to this side. The second one is through the roof. Now, the best way to prevent heat loss through the roof is for, well, I'm not going to put roof, I'm going to put loft insulation. Okay, so directly above your ceiling in your top room, what you should have foam, or often it's called, what is it? It's glass fibre, right, fiberglass. Okay, and what that does then, that prevents the heat loss. Third one is windows. And the best way of then preventing heat loss through the windows is double glazing. Now, most houses these days have double glazing, some houses even have triple glazing. Right, what that then does, that will then stop heat loss through the windows. Next one is prevent drafts. All right, so if you're ever in a room or a bedroom or anything like that, you can feel a draft. If there's no windows open, then there's an issue somewhere and you need to find where the draft is. Often it can be underneath the front door, so you can put one of those big snake things across to block it, or it can be through the letterbox, so you can put those kind of hair things across the actual letterbox itself. All right. So what I'm going to put on here is I'm going to put draft excluders. And then the final one is floors. Okay, now the best way of preventing heat loss with a floor is put carpet down. In my house we used to have wooden floors, wooden floorboards, and what you could do is you could always feel a little bit of a draft because any little cracks in the floor at all, air would then get through it. Carpet is fantastic, right? That's floors, looks like flour. Right, question number 8. Now this one is what are the 9 main energy resources, and I want positives and negatives of each one. Now a lot of these then work out quite similar, all right, but we're going to go through them anyway. So the positives of fossil fuels, okay, are there is a large resource. So basically what that means, we've got a lot of them. They're also relatively cheap to extract. Okay, so if you want coal and you want to do open coal mining, right, then what you've got to do is you literally just got to go and dig a hole and you can dig the coal out if it's close enough to the surface. It is non-renewable, which means once it's gone, and it also produces lots of pollution, especially stuff like sulfur dioxide and carbon dioxide. Nuclear, right? The advantages of nuclear is there are no greenhouse gases. Okay, and it's also, you get a lot of energy from a small amount. Okay, so a tiny little bit of nuclear energy, uranium, plutonium, you get large amounts that are actually coming out. Biggest problems is the fact that they are very expensive to build in the first place, and then when they come to their end of life, they're very expensive to decommission. All right, major pollution. Now, obviously, it doesn't happen particularly very often, right? Probably in the last 40, 50, 60 years, there's probably been 3 Mile Islands. There's the one in Fukushima in Japan, and then you've obviously got Chernobyl, right, that then caused pollutions, right? But obviously Chernobyl's then the big one. Biofuel, right? So what biofuel is, it's where you grow a plant and then you can use it as a fuel. It is renewable because what you can do is you can keep on growing it all the time, and it's also carbon neutral, which means you grow it and then you burn it, and what you're doing is when you're growing it, you're taking carbon dioxide in. When you burn it, you're giving carbon dioxide out. So it's basically carbon neutral. Problems is we need a lot of land. Okay, so if you're going to grow fields and fields and fields of plants, right, to use as biofuel, you're going to need a lot of land. Okay, and it's also the fact that it does release carbon dioxide. So even though it's carbon neutral, right, it'd be better if it wasn't. Tides. So the positives about tides is they are predictable. Okay, they're also no greenhouse gases. Alright, so we know when the tide's going to come in, we know when the tide's going to go out. The negatives are to actually set one up is expensive, and it can also alter habitats. Right, so if you think you've got to put some sort of great big dam across something, right, then there's one on the Thames estuary, and what it's going to do is when the water's coming up, when it's going in, tide comes in, it's going to affect what's after the dam, right, and then when the tide's going back out again, what's going to happen is there's more water going to stay behind the dam and it's going to take longer. So it does alter habitats. Some others, waves. Right, so waves, the advantage, now a lot of these are then going to be same, renewable, okay, so it's continuously there, and there is no waste. Okay, and what I'm going to do here is I'm going to be really boring, is I'm going to write renewable and no waste, and I'm going to write down renewable and no waste. This is no waste products, so I could put products there. No waste products. Now there are other things that we can then talk about a little bit. Solar is exactly the same, it's renewable, okay, it's infinite, and there is no waste products. And then geothermal is renewable again, and there's basically no waste product, so like no gas is given off. Right, so they're all kind of the same really. Now the negatives are the ones to then think about a little bit more. Waves are unreliable. Okay, even though you know when the sea's coming in and the sea's going out, you don't know how big the waves are going to be. It will also, big waves could cause damage. Hydroelectric power, right? So hydroelectric power is then when you've got your big dam, all right? So when you've got your big dam, the negatives are the fact to actually set one up in the first place is incredibly expensive. And also everything above the dam, the habitats are destroyed. Okay, oh, can't spell destroyed, that says destroyed. Right, now one advantage of hydroelectric power is the fact that electricity can be instant. Okay, so now another positive that you can have. So if you want electricity, what you do is you open a sluice gate, out comes water, and you make electricity straight away. Wind is unreliable. Okay, sometimes it's windy, sometimes it's not. Another disadvantage is that you've got visual and noise pollution. Okay, now if I'm ever driving up the M55 and I can see some of these wind turbines on the side of the road, or I look out to sea and there's wind turbines, I actually think they look quite cool. Right, I don't think they actually look visually, they look quite good. They are incredibly noisy, but I also know that if I had one of them in my back garden that I could see all the time, I wouldn't like it. So visual and noise pollution. Solar, to set it up on a large scale is expensive, and it's also unreliable. Okay, in some countries, like Spain and things like that, it's going to be a lot more reliable. But in Britain, sometimes it's rain and sometimes it's not, right? And very rarely sunny. And also, you can't do it in the night. Geothermal, the last one on here, right, is biggest issue is it can only be done in limited places. So, for example, it could be done in a few places in America. It could be done in Iceland, maybe New Zealand. But we couldn't do it here because the core, the heat, is too far down. It can also cause earthquakes. Okay,